Hello everyone, welcome to my lecture series on math and physics. My name is Timothy Nguyen, and in this lecture we'll be discussing differential forms and integration. So we've discussed the exterior algebra in lecture 2 and the concept of a cotangent vector in lecture 3. We're now ready to combine those two concepts to obtain the notion of differential forms, which are among some of the most fundamental objects in differential geometry. Specifically, differential forms are needed to construct an integration theory on manifolds, but also many of the fundamental equations in physics are naturally expressed in terms of differential forms, such as Einstein's equations in general relativity and the Yang-Mills equations in particle physics. So in this lecture, we'll be going over basic constructions and performing integration. And in the next lecture, we'll go deeper by covering the exterior derivative and Stoke's theorem. So just as a note to those who are tuning in, what I'm trying to accomplish in this lecture series is a compromise between a rigorous course, which would require significant self-study and preparation, and an exposition catered to those who are looking to get a sample of the subject but aren't afraid of a technical deep dive. So if there's some background material which I've left out or which I glossed over too quickly, feel free to look at the video notes or else just leave a comment. Okay, so let's go over the notion of what differential forms are. Okay, so let's begin by looking over the two basic ingredients. So we have the notion of the exterior algebra. Okay, and this we covered in lecture 2. And we also have the notion of cotangent vectors. And this we covered in lecture 3. Okay, so we're going to discuss differential forms on n-dimensional space in general, since it's easier to actually work in full generality. In the last lecture, we worked in 2 dimensions, but now we're going to step up our game and work in n dimensions. So now we're on Rn, and the basis of cotangent vectors will now look like the following. We have dx1 to dxn, and we can think of these as, well, they're the coordinate basis. I'll call them one forms for now, even though I haven't quite defined it. But we can also think of these guys as coordinate basis cotangent vector field. Okay, so recall that in 2 dimensions we had the cotangent vectors dx and dy, and now we just have a dxi for each coordinate direction. And since there's n of them, I have dx1 to dxn. Okay, so these are, well, just symbols for now. Let's try to think a little bit more geometrically using bundle language. So if I were to explain the concept of a differential form in terms of bundles, how would I do that? So I'm just going to write some notation here and explain them in somewhat of a piecemeal way. So let me just write the following. Okay, so this term here is really just a funky way of writing what's called the cotangent bundle. What's the picture I have in mind? So I have n-dimensional space, which is Rn. I'll just draw that as a line so that I can draw it. And at each point, I'm going to have a vector space, okay, which is the span of the coordinate cotangent vectors at that point. Okay, so it's an n-dimensional space. an n-dimensional vector space since Rn is n-dimensional. So this is a vector space at every point. Each point has this span of dx1 through dxn. And so that's what this cotangent bundle is. It's just this span of the dx1s to dxn at every point. And this lambda here, well, that's the symbol we use for the exterior algebra. Okay, so when I put the lambda in front of the span, then now I replace the vector space at every point with an exterior algebra at every point. Okay, so this is now a bundle of exterior algebras. And then finally, this gamma here is what's called sections. So by section, I simply mean that I'm going to pick out an element from this bundle of exterior algebras at every point. Okay, so the way one could draw this is that now we have this exterior algebra at every point. So we have this exterior algebra at this point, another exterior algebra at another point. And by a section, we just mean some choice in that vector space above every point. So I'll just draw it as this green curve, because this green curve picks out an element of this exterior algebra at every point. Okay, so that's what we mean by a differential form. A differential form is just something that lives, that is a section in this bundle of algebras. Okay, if this doesn't make sense now, I'll make it more concrete later, but I'm just starting at a very high level, and then we'll make this more explicit soon. But just to unpack this notation a little more, we can write this expression on the left-hand side as omega 0 direct sum omega 1, omega k, omega n. Okay? Recall that the exterior algebra had all these components based on how many wedge products there are. And that induces a decomposition of differential forms also into various degrees, also based on how many wedge products we see. So this omega k is what's called degree k differential forms. Okay, this is quickly getting abstract, so let's look at some examples. So we have the following examples. So a zero form is just a fancy name for a function. Okay, why is that? Well, that's because a function picks out a number for every point in our space Rn. Right? I guess I should have explained that this exterior algebra, right? Remember that the exterior algebra, let's see, so if I have the exterior algebra on a vector space, then it has different components, right? And what I mean by omega 0 is that every point of my section picks out an element of lambda 0, the zeroth part of the exterior algebra. And the zeroth part of the exterior algebra is always just R. Okay, so a function just picks out an element of R at every point x, and therefore well, that's what a function is. It gives you a number for each element x. What does a one form look like? A one form looks like the following expression. It's a sum over different components. Okay, it's a sum fix times dxi, right? So let's just make it even more explicit. I goes from 1 to n. And the reason a one form looks like that is because, well, this omega 1 corresponds to picking out an element of the degree 1 part of the exterior algebra. So it picks out something that has one wedge product. So in other words, it picks out some linear combination of these dxi's here. And that linear combination has coefficients that vary in space. And those coefficients are precisely the fix's. Okay? So the way you should think of a one form is that it picks out some linear combination of the dxi's as you move in space. And that linear combination is precisely given by the fix. It's the contribution, it's the coefficient of the dxi's. Okay, and then likewise, a two form well, at every point, you have to pick out something that has two elements that are wedged together. And so, therefore, now you have a sum that looks like this. Okay? So you have all possible choices of dxi wedge dxj. And likewise, for a general k form, we're going to have a sum over all possible indices of a choice of k indices. Okay, where dx to the index set I, if I is this tuple here, well, you just wedge the corresponding components. Okay, and well, we can assume the I1 through Ik are all distinct, because recall that if you wedge two elements that are the same, you get 0. Okay, so a differential form is just varying elements of the exterior algebra, as shown here. Okay, so why do we care about differential forms, or how might we want to intuitively think about them? It's a bit notation heavy if you haven't worked with these objects before. So intuitively, K-forms are things that you can integrate against K dimensional domains. And what I really mean here are manifolds, which I'll return to in a moment later. But essentially, you should think of as K degree differential forms, or just K forms, as things which you can integrate against K dimensional spaces. And by integrate, I mean you take that space and you return a number, right? Because an integral is something that takes an object and returns for you a number, the object being the expression inside that integral. So let's look at some examples. So for K equals to 0, well, what do you mean by integrating against a zero-dimensional object? That's sort of a degenerate case. So you can think of zero-dimensional integration as just evaluation on the set of points, because a zero-dimensional space is just a collection of points. So this is just function evaluation. For one, so one form integrates along curves, okay, because curves are things which are one-dimensional. For k equals 2, a 2 form integrates along surfaces, and etc. Okay, so a surface is a two-dimensional space, and then we have notions of higher dimensional spaces. But these examples are enough for us to get going. Okay, but before we can jump into the notion of integration, we have to do a little bit of preparatory work. In the previous lecture, I tried to lay out the fundamentals of differential geometry by focusing on 2 dimensions, just so everything could be concrete and as simple as possible. So the price for that is I now have some catch-up work to do. I want to explain some of those notions, such as push forward and pullback, in more generality, since that's what we're going to need now. So I'm going to cover push forward and pullback in enough generality for what we need. I'm also going to discuss the notion of a contraction operator for differential forms. And these are fairly notation-heavy prerequisites. So if this is a bit heavy on a first going, feel free to jump ahead and look at some of the explicit computations later, and then return to this material when you're ready. But okay, so let's just go over some of the mathematical background nevertheless. So what I'm going to need to do in order to get to integration is define the notion of push forward and pullback. But in general dimension, okay? So we did it last time for dimension 2. Well, technically we thought about it very abstractly, but my formulas were only for dimension 2 and using polar coordinates. Now I want to write down the general formula, which you can actually deduce from the abstract way of thinking we did in lecture 3. Okay, so just to write this down, so lecture 2 was n equals 2. Now consider general n. Okay, so even more generally, we can consider pullbacks and push forward when the source and target spaces have different dimension. So in general, suppose we have a map phi from some domain, some subset in Rm, and it maps to Rn. Okay, and the coordinates on Rm I'll denote by u1 to um, and the coordinates on Rn I'll denote by x1 to xn for convenience. Okay? It'll be cleaner to use different letters for coordinates on different spaces. Okay, so we have the following picture. This is Rm, and our map phi is defined on some subset U, and it maps to the target space, which is Rn. So here's a point P, and it goes to 5P. Okay, so let's look at explicitly how the push forward and pullback formulas look like in this level of generality. Okay, so we can pull back functions, and well, the expression is going to be the same because it's coordinate independent the way we thought about it. If I pull back a function f defined on Rn, then all I do is I precompose with the map phi. Okay, so f is defined on Rn, right? So f lives over here. It maps every point in Rn to a number, and then I just pull it back. I get now a function defined on U. Okay. Things get more interesting now if I look at the push forward on tangent vectors. Okay, so here I have coordinates u1 through un, and I have coordinates x1 through xn. I have this tangent vector, this coordinate tangent vector, partial u, partial I. Its push forward is going to be a tangent vector here at 5p. And the point is I can express that tangent vector in terms of the basis tangent vectors in Rn. It turns out that the formula is given by the following. So this is a tangent vector at 5p. And what I have to do is I have to compute these partial derivatives of the map phi . Evaluated at p. And I'm going to implicitly sum over repeated indices. Okay, just as a shorthand notation. This is so-called Einstein notation, or Einstein summation. Okay, so the J index is repeated, so that's implicitly summed over. Okay, so I pick an I from 1 through m. I push forward the ith coordinate tangent vector. I can express it as a linear combination of the coordinate tangent vectors in Rn. So I now have components for each of the partial xj's. And the component is given by the corresponding partial derivative of phi, the jth component, with respect to ui, the coordinate direction in question that I'm pushing forward. Okay. And the next thing to consider is what is the pullback of cotangent vectors. So now if I have a coordinate cotangent vector dx j here, I can pull it back, to a cotangent vector in the domain. What's the formula for that? So I pull back this dxj. It lives at p. How do I compute that? That expression is going to be given by the following, also in terms of partial derivatives, but it looks slightly different. Okay. I'm also using Einstein summation, but now I'm summing over the i's now instead of the j's. Okay, so j appears on each side, that's fixed, and I'm summing over the i's. So the pullback of the dxj, I'm now varying the derivative indices, this partial ui, whereas the component of phi is fixed. Okay, unlike the push forward case where the derivative index, the partial ui, is fixed because it's fixed on the left-hand side, and then I vary the component index of phi, the j, which is summed alongside the partial xj. Okay, it's kind of a mouthful to say, but the notation speaks for itself. And again, this is pretty abstract. I don't expect you to necessarily follow this if this is the first time you're seeing it, but I'm writing these just to give you a sense of of how differential geometers think about things and write things in practice. And when we do explicit computations later, hopefully this compressed notation will make more sense. Okay, so this is what push forward and pullback looks like in generality, in general dimension. Let me finish by also saying that I've talked about push forward of tangent vectors and pullback of cotangent vectors, but you can also pull back tangent vectors and push forward cotangent vectors if phi is what's called a diffeomorphism, if it's 1-to-1. Okay, so let me just write that. You can also push forward cotangent vectors and pull back tangent vectors if phi is invertible, i.e. what's called a diffeomorphism. Basically a map that you can invert, and both it and its inverse are smooth, so you can take derivatives of the map phi and derivatives of its inverse. Okay, I just wanted to note that, but I won't be writing the formulas. The formulas are very analogous. And they involve the inverse, which is why you need this invertibility criterion. Okay, and so why did I need to revisit these notions of push forward and pullback? It's because these are the basic building blocks, and now we can understand how to pull back differential forms. So we can pull back differential forms by, how do I say it? Passing it through the wedge. Okay, so let me just put a bullet here and a bullet here. So what do I mean by that? So if I now want to pull back some expression like dxi1 wedge dxik, then all I need to know is how to pull back the individual dxi's, which I already know how to do because that's precisely this formula right here. Okay. And so all I have to do is pull back the individual factors, and this will give me my pulled back differential form, right? So this is a differential form that's of degree k, right? Right, so it has k terms and k-1 wedge products. Each of these dxi's is a 1 form, and I pull back each of those. Each of these is also a 1 form. And altogether, this is also a degree k. Okay, so it's a lot of notation, but it's all somehow decomposed into simpler pieces. So once you know the wedge product and once you know how to pull back 1 forms, you know how to pull back k forms. That's the point. Okay, and the next piece of background information or basic construction information that we need is something called the contraction operator. Okay, so let's do another bit of review. So we have our set of cotangent vectors dxi from 1 to n, and that is recall, is the dual basis to our set of coordinate tangent vectors, right? What does that mean? It means that if I take a dxi and I evaluate it on a partial xj, well, I get 1 if I is equal to j and 0 otherwise. All right, so let's just be extra explicit about this example. All right, so in dimension 3, at every point in space, I have my coordinate tangent vectors in each of the coordinate directions. And then I also have dx1, dx2, dx3, the coordinate cotangent vectors and then dx1 evaluated on partial x1 is equal to 1, and then dx1 evaluated on the other coordinate tangent vectors is 0. Okay, and likewise with 2 and 3. Okay, that's what it means to be a dual basis. Okay, so what is a contraction operator? So let's first start by rewriting this expression here using a slightly different notation. So we can rewrite this expression as partial j, and then we're going to use this this sort of right angle symbol, okay, to mean the expression here. So this is the contraction operator. And all this is literally saying is that we're going to take this tangent vector and contract it with this cotangent vector. So it's exactly just this evaluation we have in this first expression. It just feeds the this tangent vector into that cotangent vector. Okay. So why are we using this notation? It's because it extends to differential forms now, not just one forms. Okay, so we now can define contraction for all degree forms. Actually, let me first back up. So if I have a general tangent vector, so v equals vi partial xi, okay? So again, I'm using Einstein summation, so the I is summed over from 1 through n. So this v is a general tangent vector. It has n components. And then if I do v contract with dxj, then this is just vj, right? Because dxj will pick out the component of the tangent vector that, well, for which I is equal to j, right? It's this dual basis property here, precisely this. Okay, so this I just wanted to emphasize just so we're all on the same page. Okay, and so when we now define the contraction operator for general degree forms, how do we do that? So now v is a tangent vector. I contract it, say, with some, say, differential forms which might be expressed as the wedge of two smaller pieces. How do I define this contraction? Well, I can break it down into its definition on smaller forms. So I'm defining the contraction operator essentially inductively on the degree of the form. So what it is v contract with the form on the left is v wedge the first piece omega wedge eta plus another term which picks up a sign which is minus 1 to the degree of omega. So this is going to be plus if omega is even degree and odd, and sorry, minus 1 if omega has odd degree. And then it's omega wedge v contract with theta. Okay, let's just do a computation because I think it'll be a lot more clear. This is maybe a bit abstract, so let's just do an example. Change color here. So if I do v wedge dxi wedge dxj, well, that's by the above formula, v contract with dxi, wedge dxj, minus, because dxi is a 1 form, so it's degree 1, which is odd, minus dxi, that's an I, wedge v contract with dxj. Okay, and then, well, this is just the function vi, and then I can just drop the wedge because wedging a function with the 1 form is just multiplication, and then this is minus, this becomes vj, right? This is vj, and then I'll just go ahead and move it to the front because functions and 1 forms commute in terms of multiplication. Okay, so as you can see, this is what the formula looks like. Note that this, note that we contracted a vector with the 2 form and we got a 1 form. So in general, contraction lowers degree. Okay, so contraction maps omega k to omega k minus 1. It lowers the degree. So here, k was 2. And let's just do finally one more example for k equals to 3. J, which let's say dxl. So we have v wedge dx, sorry, v contract with dxi, wedge dxj, wedge dxl, minus, yeah, I'm actually applying the above formula sort of iteratively, so there's actually 3 terms. Okay, now I have the middle term, and then finally I have the last term. And since I had to move v past 2 1 forms, I get 2 minus signs and then an overall plus sign. Okay, and then overall my final expression is vi dxj wedge dxl minus vj dxi wedge dxl plus vl dxi wedge dxj. Okay, so why do we care about contraction operators? Well, there's several reasons, but let's focus on the ones we care about most immediately. Well, the first is that we can, we can extend to wedge product of tangent vectors. Extend the contraction operator, that is. So in other words, now I can define this operation. Okay, so the VI's are all tangent vectors. And if I want to contract the wedge of k tangent vectors into some differential form omega of general degree, then I just go from left to right. So I just contract v1 into omega vk. Okay, so I just contract from left to right. And okay, so that doesn't really answer the question. I just explained how you can generalize the contraction operator. But we're going to need this operation when we do integration. So there's going to be a lot of interaction between tangent and cotangent vectors when we do integration differential forms, and this contraction is going to show up, as we'll see soon. Okay, so let's finally get to the notion of integration. And let's focus on 2 specific examples, the integration of 1 forms and the integration of 2 forms, since if we understand those, then that will generalize to the higher dimensional case, essentially, just with more components and indices. Okay, so let's do integration of one forms first. And to be extra concrete, let's say focus on the dimension n equals 3 case. Okay, so I'm going to look at a one form in dimension 3. So, but again, n could be arbitrary, but I'm just doing this just so we can be more concrete as a relief from the abstraction that we just went through. So now a one form has 3 components, functions multiplying each of the dx1, dx2, and dx3, f1, f2, f3. Okay, and let's focus on the simplest case first, which are, well, we need to integrate over something, and the thing we're going to integrate over are curves, and the first easiest case are coordinate curves. By coordinate curves, I mean curves that just move along one coordinate axis. So for example, suppose this were my curve, and well, it starts at, say, A, and it has its x2 and x3 components fixed, and it goes to B, again with the constant x2, x3. So this curve moves parallel to the x1 direction, or moves along the x1 direction. And in this case, if this is my general one form omega, then the integral of omega along gamma, so this is gamma right here, well, it just actually becomes a one-dimensional integral where I pick out the component that's in front of the dx1, so that's the function f1, and then I integrate with respect to x1 and from a to b, and I keep the other 2 components, x2 and x3, fixed. Okay, so what's key here is that only the x1 variable is changing. That's why I have a dx1, and it goes from a to b because those are the 2 limits given by the curve gamma. So you can think of essentially dx1 as sort of, well, this kicks out the x1 direction. Okay, and this is likewise for x2 and x3 directions. Okay, so if I had curves going in the x2 and x3 direction, I would just apply the same formula. I'd now have the corresponding f2 or f3 and do that integral. So essentially, in this very simple case, if you give me coordinate curves, the way you would integrate omega along them is just to do an ordinary one-dimensional integral determined by that coordinate curve. Okay. That's not that interesting because in general, curves can move around in complicated ways. Right? So I really should be looking at general curves. And this is where things get a little bit more interesting. Right? So how do I integrate if I have a curve that, you know, just does something like that? Say, this is my curve gamma. Actually, let me back up a bit because I realized I didn't explain something in the coordinate case that is going to be very important actually going forward, which is that of orientation. Okay, so let's look at orientation. Notice that this curve goes from left to right. Right, so this was from how do I say? Yeah, let's go left to right. If instead I had gone from right to left, the integral would pick up a minus sign. Right, so if I had parameterized gamma is going from right to left. So let's call this gamma twiddle. And then the integral of omega over gamma twiddle would go from b to a. It's the same integrand. But remember the calculus rule that I can switch the two limits of an integral and I will get a minus sign. And so indeed, that's what I get here. Okay, so whenever we integrate along a domain, we have to choose an orientation, which in one dimension is just a consistent direction, either left to right or right to left. This will become more important when we go to higher dimensions, because the way in which we specify orientations was, as explained in lecture 2, we have to choose basically a maximal set of independent directions. So in the case of surfaces, we have to choose 2 directions, and that will give us a choice of sign. Okay, but we'll cross that bridge when we get there. But I just wanted to emphasize that when we integrate, we also have to choose orientations. And in this case, it's easy to visualize because it's just the way the curve is parameterized, left to right or right to left. In case the curve is moving in many directions, the notion of left and right only made sense in this picture, but basically there's always sort of whenever you have parameterization in one direction, you can always reverse the curve, and that gives you the opposite orientation. So it's not so much left to right, but it's just there's always a way to parameterize a curve, and then you could just reverse it, and that gives you 2 different orientations. And the corresponding integral will change sign if you do so. Okay. So now for general curves, how are we going to do integration? So, well, what does it mean to be a curve? It means that gamma is really a map from some interval a to b in R. Maps an interval a to b in R to R3, right? Because this lives in R3. And really what gamma is that gamma is a map from this interval to R3, right? So this lives in R. And so the way in which we're going to define this integral is just by pullback. So if omega is a 1 form on R3 and we want to integrate against gamma, then what we do is we pull omega back by gamma, and then now this just becomes an ordinary interval, an ordinary one-dimensional integral, which I can just write like this, or rewriting this in more calculus-like notation in terms of a function times a differential dt. This is also the same as omega evaluated on the derivative of gamma, or this is also the same thing as gamma push forward partial t, okay, times dt. Okay, so this gamma dot is the same thing as a push forward. Okay, so I'm just rewriting this integral in several ways just so that perhaps one of them makes the most sense to you, but these are all equivalent. Okay, and notice by the pullback, we've reduced this case of the general curve to a ordinary one-dimensional integral on R, right? So in other words, this sort of complicated looking integral here, this curve that's winding about generally in R3 or in general Rn, now becomes what looks like an ordinary calculus one-dimensional integral on the right using pullback. And this is going to be a general feature of our integrals. We can decompose it into bits which look like standard integrals on Rn. Okay, but let's focus on the one-dimensional case for now. Let's do an explicit computation so that all this notation can become operationalized and we see how it actually works in practice. So let's do the following example. To be even more simple, let's do n equals 2. So now I have a curve in R2. Let it be the curve which goes along the upper part of a circle of radius r. Okay, so gamma of t is, well, x of t, y of t, but in our index notation, let's call it x1 and x2 of t, and that's given by r cosine t and r sine t, right? So t is in effect the angle theta, and this is r cosine t, r sine t, right? And what is the differential form that we're going to integrate along this curve gamma? Let's let omega r1 form be the polar coordinate one form, just d theta. And well, if you write out what d theta is in rectangular coordinates, in the standard Euclidean coordinates, it looks like the following. And again, writing it in terms of our index notation, let's call this x2, this is x1, r squared, and this is x1, x2. Okay, and recall r squared is just the sum of the squares of the rectangular coordinates. Okay. Oh wait, hopefully this isn't confusing. The outer 2 is a square, and this inner 2, that's an index. Okay, so just thought I'd make that remark. But okay, let's move along. So what we wrote above was that if we want to compute this integral of d theta along gamma, what we should do is compute this pullback and integrate up from 0 to pi, right? Because this t is going from 0 to pi, right? That's exactly going to trace out this upper semicircle. So what is the pullback of d theta by gamma? So we have to use the formula that we wrote earlier, okay? And if we unpack that, this is what we get. So we have to, well, evaluate all these coefficients at time t, and then we also have to pull back this one form. That's given by that. And then likewise for the other component. Okay, where these ddt terms, oops, I forgot to put that term there. Okay, so I have these ddt terms. That's coming from these functions of time here, right? That's how gamma enters into the picture. Okay, and so let's just substitute in the expressions, actually. So, okay. So when we substitute in at time t, then we just make use of these expressions, right? When I say at time t. So we have r cosine t r squared. And then for the derivative terms, when I differentiate dx1 with respect to t, I'm going to get a minus r sine t, and then plus, likewise for the second term here, I'm going to have, sorry, this is an x2 over here, and x2 is the sine term. And then the x1 is going to be the r cosine t r squared. And then the dx2 dt, that's going to be r cosine t, because we're differentiating sine, which is cosine. And likewise, for the dx1 dt term, we differentiated cosine, which is why we got minus sine. Okay, so simplifying all of this, we finally get, well, the r squareds are going to cancel out. What we're left with is a sine squared t plus cosine squared t dt. But sine squared plus cosine squared of any input is just 1. So then we just get dt. Okay, and so this becomes just this integral from 0 to pi of dt. And we know how to compute that integral. It's just pi minus 0, which is pi. And that makes sense, right? Because if we think about it, what is this integral on the left saying? It's saying, what is the change in theta as I move along gamma? That's intuitively what this integral is saying. And well, we know what the change is. It's the change in theta from here to there, and that's pi. Okay. So, and likewise, if we had gone in the opposite direction, if we had changed our orientation, instead of going from 0 to pi, we'd go from pi to 0, and then we get minus pi instead of pi. Okay, so that's how this computation looks like, thought about in terms of the notation and concepts we introduced earlier in generality. All right, so let's wrap up this lecture with a discussion of how to do integration of two forms, and that's already going to highlight the essential technicalities of integration for general degree forms. So let's do integration of two forms. And also, just to be ultra concrete and simple, let's look at the case where n equals 3. So I can write my two form explicitly as a function f12 times dx1 wedge dx2, and likewise with the other components. And as before, I can break it up into two cases for how to do integration. So in the first case, I can integrate over especially simple regions, which are so-called coordinate regions. So I'm in a highly specialized situation where, say, my two-dimensional region of integration has, let's say, the x3 component is constant, right? So I'm in this x3 equals constant, which is a hyperplane, and in this hyperplane is my region omega, right? And in that case, if I integrate omega, little omega, the 2 form, over this two-dimensional domain big omega, well, because x3 is constant, only x1 and x2 are varying, and that's precisely what this component is going to pick up. These other components are only non-zero when I have some x3 components, but because x3 is constant, they're invisible essentially when I integrate over omega. So I'm only going to get a contribution from this 1-2 term. Okay, this is sort of analogous to the case of curves, where if I only go along the x1 direction, then I pick up the dx1 part, and likewise with dx2 and dx3. This is the higher dimensional version of that. And so, sorry, and to write something more specific. I meant to write x1, x2, and x3 is fixed as z. And then now I do an ordinary two-dimensional integral from multivariable calculus over this omega. Okay. So this integral on the right-hand side is what you will have seen in multivariable calculus. This is just an ordinary two-dimensional integral. Sometimes people will write a double integral to emphasize that it's two-dimensional, but just to be consistent, I'll just write one integral, and the domain will tell you how many dimensions it is. Okay, and there's actually a plus or minus sign that depends on the orientation. Okay, so I've been using, I guess, orange for orientation. And it's analogous to how we had orientation for the case of curves. Is the curve moving one direction or the other direction? Now, how do we think about that in terms of surfaces? So if you go back to lecture 2, remember that an orientation is given by a choice of a top exterior power of a corresponding space. In this case, it's the top exterior power of a spanning set of tangent vectors to our domain. Since it's living in a coordinate plane, it's somewhat relatively easy to describe or how to think about this orientation. So we can say that there's two choices of orientation. There's the plus choice, orient via, let's just say x1 followed by x2, and then there's the opposite orientation, right? Orient via x2 followed by x1, right? So if I have x1 followed by x2, I'm going counterclockwise, and if I have x2 followed by x1, then that's counterclockwise. So it's a notion of handedness, right? Clockwise or counterclockwise. That's the two-dimensional version of this element of the exterior algebra and the corresponding sign you get. So look back at lecture 2 if you need a refresher on that. But in 2 dimensions, you could think of it as clockwise or counterclockwise. And basically, if you choose the orientation that's compatible with this 2 form here, right? This 2 form has a dx1 before a dx2. And so likewise, the orientation on omega that's going to give you a plus sign is the one that's x1 before x2. And if you had written this like so, right? This guy is the opposite of this, is a minus sign of that, because whenever you switch 2 elements in the exterior algebra, you pick up a minus sign. And that's consistent also with which orientation will give you a plus or a minus sign. So if you switch the differential form from dx1 to dx2, and you switch the orientation of omega from x1, x2 to x2, x1, you get 2 minus signs and they cancel out. Okay, so there's basically always kind of 2 ways in which signs can occur. The order of wedge products in the form omega itself, and then also the orientation of big omega. And when they're consistently aligned, you're going to get an ordinary integral with the plus sign, and if they differ by a swap of the directions, you're going to get a minus sign. Okay, so that's how you can think about how these signs work out. Okay. Actually, I should also mention something a bit subtle. We talked also about the Mobius strip in the lecture 2, and a peculiar thing about the Mobius strip is it's not orientable, okay? Meaning that you actually can't choose a consistent orientation because of the way the Mobius strip is designed, right? You have this band that gets glued upside down, right? You take a strip and you glue opposite ends in a reversed way, and because of that, you can't consistently choose an orientation, essentially. So I should note that integration of 2 forms, or integration in general, requires you to have an orientable space. I'll write that down more precisely later, but I just thought I'd mention that now. So this construction will fail if you try to integrate over the Mobius strip, precisely because you can't choose this orientation consistently everywhere. Okay, so that's maybe a comment that I'll expound upon later, but let me just move on now before returning to that. Okay, so this is how we integrate over coordinate regions. What about for general surfaces? Right, so a general surface, it's just going to do its own thing, right? So it's going to look like a sheet locally, and then it's just going to, I don't know, bend all around. Okay. So by a general surface, I mean manifolds of dimension 2, and then possibly, let's say, manifolds with boundary, say. Okay, that's just a more sophisticated terminology for those who want to go further down that route. But you could just think of a manifold, a two-dimensional manifold boundary as roughly what this picture I drew here. It looks like locally like a two-dimensional sheet, and it might have some boundary, just because our regions of integration are finite in extent. Okay, so how do we integrate over this, right? It's not obviously, I mean, it's obviously not one of these coordinate regions. It's varying in all sorts of directions. But we can use the same idea that we had in the 1D case. Basically, we want to use pullbacks to reduce to 2 dimensions. The pullback is going to be trickier in 2 dimensions because surfaces are more complicated than curves. So we do the following. Well, we can always split up our integrals into little pieces, or rather our surface into little pieces, and do the integrals on those individual pieces. So we can imagine, slicing up our surface into these patches, and on each patch we can do a pullback. Okay, so here's this patch here. Okay, so omega is this entire surface, and then here I have this shaded region R, and then it's on this little r that I can use what's called a coordinate chart. Actually, draw the arrow the other way. Phi, and here phi is defined on U, which lives in R2, 2 because our space is 2-dimensional, and this goes to R, right? And this is going to be this diffeomorphism where we can pull things back or push things forward. So the way in which we can integrate on manifolds in general, and this actually extends to all dimensions, this idea. Namely, we want to know how to make sense of this expression. What we do is we now write this as a sum for each of these disjoint regions, okay? Because an integral is just the sum over the integral over the individual disjoint patches. And then on each of these, we can do a pullback. Let me call this U sub R for the rth region. Okay? And each of these individual terms we can compute, because now this is a 2-form, integrating a 2-form over 2-dimensional space, and that's just now an ordinary 2-dimensional integral. And returning back to the issue of orientation, right? So we need sigma to be called what's orientable to be able to sum pieces with consistent choice of sign. Okay. So basically, since each of these pieces has is possibly ambiguous up to a choice of sign, so long as we can consistently choose that, which we can't do on the Mobius strip, but we can do for the surfaces which aren't like the Mobius strip, then we can make sense of this integral. Okay, so this is the toolkit for how you do integration in general, a general k-dimensional form on a general k-dimensional manifold or a k-dimensional space. Okay, it's this idea of chopping it up into small pieces, pulling it back to Rk, in this case k equals to 2, and then doing the individual integrals. Let's conclude by actually doing some explicit examples where we can become more comfortable doing this computation. Okay, let's first begin by computing the area of a disk, but in a somewhat roundabout way to illustrate some of the concepts that we've learned. Okay, so it will be a bit roundabout. What I'm going to do is look at 3 dimensions as before, but my disk will be in this hyperplane given by setting the x1 coordinate equal to 1. Okay. So this is the x1 equals 1 hyperplane. And then I'm just going to put a disk centered along this axis inside this plane. Okay, and it's going to have radius r. So that's going to be my domain of integration omega, big omega, and then my 2 form, little omega, will be x1 and dx2 wedge dx3. Okay. And so what's this integral? Little omega against big omega. Okay, so because we're in the coordinate situation, we're in this coordinate region case, right? Our plane is indeed spanned by x2 and x3, so this is just going to become an ordinary integral over this disk. X1 just becomes the constant value 1. We're just holding it fixed, and then we have dx2, dx3 over this region where in polar coordinates little r is bounded by big R. Okay, so I'm just thinking of everything now happening in 2-dimensional space where the first coordinate direction is x2 and second coordinate direction is x3. Okay. All right. So now we've this integral here is exactly computing the area of a disk of radius r. Right. It's just the usual area form, dx2 dx3, restricted to the region given by this disk. How are we going to compute this integral? So we can use polar coordinates and pull this back to an integral that's just an integral over a rectangular region, which makes it easier to integrate. Okay, because technically we could evaluate this integral quote unquote directly by let's say breaking up these the disk into smaller and smaller regions and then approximating it, right? So, sorry, let me draw this bigger. So if I have some region, I know how to compute integrals of rectangles, right? Because the area of a rectangle is just length times width. So the area, length times width. The problem with the irregular shape like the disk is I don't know how to add up the areas of all these rectangles straightforwardly, right? Because they have to become smaller and smaller as I get to the boundary. And it's not clear how to do that limiting procedure. So what one typically does is one does a good change of coordinates in which one can get into a situation where the integral is over a rectangular region, and then it becomes easier. So let's see how that happens. In polar coordinates, okay, so let me erase this. Right. The point is that in polar coordinates, so this map is now, let's call it phi. Then right, our angle goes from 0 to 2 pi. This is theta, and this is r, and our radius goes from 0 to capital R. And we can ignore this sort of boundary region which corresponds to the origin, just because it has area 0, right? A point has area 0 and a segment has area 0. But other than that, in polar coordinates, the disk looks like a rectangle, right? Because we can vary the radius from 0 to r, and we can vary the theta independently from 0 to 2 pi. So that's the advantage of using pullback to switch, well, this simple looking 2 form, which has a complicated region, this disk. What we're going to do is we're going to get a slightly more complicated 2 form, but an easier region. What we're going to need to do is write this integral as phi star of dx2 wedge dx3. It's important to think of it as a wedge product now, because that's going to affect the formula for the pullback. And we're going to pull it back to this product region V, right? So V is this rectangle. And now what remains to compute is what exactly is this pullback of this area form. And if you've studied multivariable calc, you know that you're going to get what's called some kind of Jacobian term. And we're just going to work that out explicitly right now. Okay, so in polar coordinates, x2 is equal to r cosine theta, and x3 is equal to r sine theta. And if you think about that and the formulas that we had earlier for pullback, then phi star dx2 will be cosine of theta dr. We differentiate with respect to r. And then when we differentiate with respect to theta, we get r minus sine theta d theta. Likewise, phi star dx3 is equal to theta dr. And then when we differentiate theta, we get r cosine theta d theta. Okay, so if we have these formulas there, then when we expand this out, then we're going to get, right, the phi star just goes right through the wedge. Okay, and when we wedge, well, the only terms that survive are going to be the cross terms, right? Because when we wedge a 1 form with itself, it's 0. And so if we only look at the cross terms, oh, right, this should be a plus. Okay. So we're going to get an r cosine squared theta dr wedge d theta, and then a minus r sine squared d theta wedge dr. Okay, but d theta wedge dr is minus dr d theta. And so we can switch the order of those 2 terms at the cost of a sign, and then what we'll get is r cosine squared theta plus r sine squared theta dr wedge d theta. And well, that's just now going to be r dr wedge d theta. And so now we just get this double integral that splits. because V is a rectangle, and because our pullback form is so has such a simple expression, this right the thing occurring in front of the dr and dtheta is just a nice separable expression. It's just in this case it's just r. Then this two-dimensional integral really is a product of one-dimensional integrals. And we can evaluate this, and then we're going to get pi r squared. That's our final answer. Okay, so maybe let's just quickly go over the computation again. It worked out quite nicely. So we wanted to compute this integral of a 2 form over our region omega. And I rigged it so that it ended up being the area of a disk because it was exactly placed at x1 equals 1, so this weight becomes 1 and not some other multiple. If we had shifted the plane, it'd become some multiple of the disk, that multiple being the value of x1, but okay, it's 1 in this case. Then we have, well, technically this is already, an expression that we like because it looks like an expression we've seen in multivariable calculus. It's just that to calculate that explicitly, we just need to do a change of coordinates, which also illustrates how pullback tells us how the area form changes under a change of coordinates. So in calculus, there are many formulas. In multivariable calculus, there are many formulas. And what this example illustrates is how all those formulas, or at least the formula that we're thinking about in this particular case, how area forms transform, can be understood in terms of pullback. Okay, so indeed we pulled back to this simpler region V in polar coordinates, and it picked up this R factor. Right. So what was sort of a standard, just a product area form in one coordinate system became not a product. It didn't become a coordinate area form. It picked up this weight R, okay? And that just came up from this pullback formula. And anyways, so that just was a computation, but the point is that now it's simpler to do this integral in polar coordinates than in rectangular coordinates, and we got the pi r squared. Okay, so it worked out quite nicely. All right, last computation. Let's compute the surface area of a sphere. Okay, so this is also the k equals 2 n equals 3 case, right? Because we have a two-dimensional surface sitting in three-dimensional space. And for the sake of simplicity, I'm just going to compute the upper half of the sphere and then double it to get the area. Okay, so it's just by symmetry, right? The top and the bottom halves have the same area, obviously. Okay, so what we need to do is to compute. So let's see. So the area of S2 will be twice the area of omega time the integral over omega of this 2 form omega, where omega is sort of the area form on S2. So there's a differential form such that when I integrate it, it's going to give me the area. Now this requires a bit of reasoning to think about what this is, but it's not too hard to convince yourself that what it is that it's the unit normal to the two-sphere contracted with the standard volume form in 3 dimensions. Okay, if you sort of think about that, I hope that's reasonably intuitive, because the volume form d capital V one can think of as dx, dy, dz. Okay, so I'm going to switch back to XYZ just because the notation becomes a little bit easier to keep track of. But really, I can choose any orthonormal frame, right? Any sort of three directions. I don't really care if it's really XYZ. I can rotate it these three directions, and the product of the one forms in each of those directions, the wedge of all three of them, will still give me a volume form. Okay. And so if you think of an area form as being something that weights the tangent space of the sphere, infinitesimally, it gives the correct area of this little square that's tangent to the sphere. Then what you're doing is you should think of dV as sort of a dn wedge dA, where dA sort of weights this area correctly, and then you need a dn which is orthogonal to the dA, so that you have an orthonormal set of vectors that you're wedging. And so this is the sense in which this formula holds true, right? Because if I do the unit normal wedge dV, that n wedges with dn and gives you 1, and then the other term vanishes because n is perpendicular to a. So this other term will be 0. Okay, so this is maybe a bit of heuristic reasoning, but it could be made rigorous. But I'm just sort of illustrating this just to show you the kind of reasoning that goes into this, even if it might be a bit incomplete relative to the details that we've discussed in this lecture. But okay, if you accept what I wrote here, then we can continue forward with the computation. Okay, because then let's go ahead and go forth. So now this is, the unit normal is going to be this vector. Okay, because it's the vector that points in the direction x, y, z, and it's going to have unit length because this is the unit sphere. So I should have mentioned this is radius 1. Okay, so this is unit sphere. And we're going to wedge this with dx, dy, dz. And this is over this upper dome part. Okay, so let's continue. So we do the contraction. We're going to get x, dy, dz. And then get a minus y dx. I should put a wedge. See? Plus z dx y. This follows from the contraction formula we wrote earlier. And you pick up signs depending on how many times you have to move this tangent vector to the appropriate one form that can evaluate it non-trivially. Okay, so we're left with this. And now we're going to do this pullback to simplify this expression. So let phi be the map which maps this two-dimensional disk to the sphere by just pushing the disk up into the sphere, right? So in other words, phi of xy is x, y, and then it just recovers the z value of this dome, which is a graph over the disk, right? So it's going to be square root of 1 minus x squared minus y squared by essentially the Pythagorean theorem, right? We need this vector to have length 1, and so the z coordinate is determined by that and given by that expression that I just wrote. Okay, and so we want to pull back. Oops. We want to pull back to the disk underneath the dome. Okay, and now we just need to compute this pullback. And if you look at the expression for the pullback, the only thing interesting going on is with the z components, right? Because phi is the identity on x and y, and it's only interesting, non-trivial, in this z component. Okay, so what this ends up being is this is going to be x dy wedge dz dx dx minus y dx wedge dz dy y plus 1 minus x squared minus y squared dy. Okay, technically dz has some other terms, but when there's a dy wedge, I don't need to keep the dy term here because it's just going to cancel out in the wedge product. Likewise, I don't need to keep the dx term here when I wedge with dx because that's going to contribute 0. Okay, so at this point, it's just a computation, and we have to shuffle minus signs around and things like that. I'll leave it as an exercise that if you work this all out, what you'll end up getting is the following expression. Okay, so that's just an exercise, some simple algebra. Okay, and now we're almost done. We just do the same polar coordinates change of variables like last time. Then we're going to get this integral. The dx wedge dy becomes a r dr d theta. And we have two separable, we're in the separable case where we could just compute the integral separately. And so we're going to get a 2 pi, and in this case, we just use the fundamental theorem of calculus. One to 0, and altogether, the answer is 4 pi, which indeed is the surface area of the unit sphere. And by homogeneity, if the sphere has radius r, then the surface area has the surface area is 4 pi r squared. Okay, so this is this confirms that we did our setup of the integration correctly. We recovered the area of the sphere. Okay, wow, so covered quite a lot. It was quite abstract. I hope that these explicit computations at least reveal how some of the algebra gymnastics works out, even if I didn't go over the details as much as I could have. This is, of course, a pretty advanced material that requires quite some time to do properly, and of course, within the limits of a YouTube video, well, I could only cover so much, but hopefully I was able to convey some of the basic aspects of differential forms and how to integrate with them. And so next time, we'll go a little bit deeper. We'll cover what's called the exterior derivative, so we can talk about Stoke's theorem. And we need Stoke's theorem to talk about, well, let me start writing this down. So we need Stoke's theorem. Why? Well, from the point of view of gauge theory, Stoke's theorem is what allows us to think of, relate infinitesimal parallel transport with curvature, at least in the so-called abelian setting. So that's how Stoke's theorem can be give us insight into gauge theory. And also, just as an aside, as a sneak preview, what Stoke's theorem also allows us to do is to unify various vector calculus theorems. Or multivariable calculus theorems. In multivariable calculus, in three-dimensional calculus, you learn a Stoke's theorem. You also learn various other things, the Green's theorem or the divergence theorem. They're actually all manifestations of a single Stoke's theorem. And so we'll see that next time. Okay, so we've covered a lot. Thanks for tuning in, and I'll see you all in the next lecture.